Okay, has everybody checked in? Because we want to make sure, especially if you're getting college credit, that you're checked in so that you get, credit for attendance. Has everybody done that? Okay, and again, my name's Gary Albright. Maybe I should have sent an email. I forgot to tell Katie, but I had to switch. We were originally today going to do a lecture on superconductivity, but the person who was going to do that had to go away this weekend for a job interview because he's not a permanent faculty here, and so he asked me to switch with him. And so, unfortunately for you guys, I'm going to sort of do the lecture and at least be helping out with the activity. I didn't mean to do both of these things this week, but because no one else could switch with them for today, what we're actually going to do, and I think in some ways this kind of works out, is I'm going to do what was originally scheduled for February 28th, which is on the Big Bang. Okay. Now next week we'll be learning about black holes, and so actually this sort of kind of puts all the astronomy a little bit more together, and then later on we'll be doing some other topics in physics. So we're switching gears. So if you were excited about superconductivity, I hate to mess that up, but we are going to be talking about the Big Bang today. Okay, so has everybody checked in already and has their t-shirt? You should have also, if you hadn't, if this is your first time you're here, we have t-shirts and then a planisphere. Now, during the activity, there's a couple of interesting things happening later this week before I see you again that I'm going to alert you to, like the full moon is on Tuesday night. Of course, we all know that Groundhog Day is on Monday, where some rodent in Pennsylvania predicts the weather, which I find absolutely delightful. I don't know why we do Groundhog Day, but I like it. And so is there any questions before I get started? Is anybody awake? I realize Saturday morning I'm in the same boat here. Now, is this too many lights? Because I can probably turn some of these off so that we can see this a bit better.
94065745993.
What was that?
It was the phone. Sorry.
I don't
anyway.
know what this thing is.
Oh, yeah.
Do we all feel like we can see this all right? So are we okay with the lighting? Okay. So what we want to talk about is, I'm assuming that all of you, of course, it's hard to know that the theory that we now have that currently explains the origin of the universe and everything is called the Big Bang Theory. So what I want to do is I want to talk about why did people come up with the Big Bang Theory? And what sort of observations led people to think that this was a good idea? Because all science is based on observation. It wasn't like somebody came up, well, maybe the universe started with some Big Bang, and then they went out looking for observations to support that. What happened was we were looking as humans at the universe and came to the conclusion that something like the Big Bang must have happened. So we want to talk about what sorts of things were they seeing that led them to this conclusion. Now, it turns out that when the Big Bang happened, the only elements that we think were made were hydrogen and helium. And hydrogen was like 91 out of every 100 atoms in the universe, and the other 9 atoms were helium. Well, since helium doesn't do anything, helium always exists as an isolated atom, one way to think about the universe is this. The history of the universe can be summed up like this. Hydrogen is a light, odorless, colorless gas that if given enough time turns into people. So if we're to believe what scientists tell us, the universe started at some time in the past. It was mostly hydrogen. Let's forget the helium because helium is totally standoffish, doesn't do any chemistry whatsoever. And so the only atom that was around, there's a little bit of lithium, that could do something was hydrogen. And so somehow, since the origin of the universe until now, that hydrogen has turned itself into me and you. Right? Can you see that seems like kind of far-fetched, that hydrogen has just quietly assembled itself into human beings? Okay, but so what we're going to try to do is fill in some of the gaps. I think this is kind of an interesting way to think about the universe, at least in my opinion. So we're going to try to fill in some of the missing parts of this statement. Okay, and so the idea is what caused the Big Bang, and I'm not going to try to explain that at all, because nobody really knows why the Big Bang happened. I mean, the way science works is, let's pretend this thing called the Big Bang happened, and can we explain everything from that? Now, there's various reasons why we can't explain it, because the laws of physics, as we know them, didn't exist before the Big Bang. So it's kind of hard to imagine what the conditions of the universe were before that time. So we're going to start with the fact that, okay, we don't know what caused the Big Bang, but if we just somehow imagine that this did happen, then can we explain the way the universe is? So the idea of the Big Bang, which I think is a nice sort of poetic way to put it, is rippling still water where there is no pebble tossed nor wind to blow. So in other words, the Big Bang just happened without seemingly any causal agent, like this ripple that just happened due to nothing. Okay? Now, I realize that's kind of a hard thing to swallow, but the idea is, what you do is you backwards engineer this or reverse engineer and say, well, everything can be explained by this notion of the Big Bang, and if everything can be explained, then you just have to sort of say, well, it must have happened. I mean, why, we don't know. And of course, we do sort of need to leave, it's not that surprising that, like every question about the way the universe is hasn't been answered yet. Because the universe is probably the most complex thing there is. Well, maybe besides the human brain. And we're not even 100% sure if our brains are sophisticated enough to actually understand why the Big Bang happened. Like, we don't know. Like, there's limitations on, like, potentially what we can and can't understand. So anyway, so let's, if we go back to the very beginning, okay, there was this thing called the Great Nebula Debate. Okay, and starting with Charles Messier, who was a French astronomer, and what he did was he was looking for comets, because looking for comets is, I guess, a fun thing to do. And so he was scanning the skies with his telescope, looking for comets. This was after Halley's Comet had been, how Edmund Halley, told people that comets keep coming back. Comets were known to be harbingers of potentially bad things happening, and so people were very interested in comets back in the in the 1700s. Does anybody know that there's a famous American who was born when Halley's Comet was in the sky, and that was in 1834, and then he died when Halley's Comet came back 76 years later in 1910? What's that?
Mark Twain.
Yeah, Mark Twain, Samuel Clemens. And he was actually proud of this fact, because since comets were sort of like, things of like with sort of bad reputations, you can imagine Mark Twain sort of took some pride in that. So anyway, and so what he did was he was looking through the skies, and every now and then he'd come across some, when you have a crappy telescope, a galaxy, a star-forming region, a star that's blown up, which is a supernova, or a star-forming region, all of these things just look like little hazy, or a comet, just look like little fuzzy patches of light in your telescope. It wasn't until, we're all spoiled by, the Hubble Space Telescope, where you get these fantastic pictures of galaxies and comets and all these other things. Back in the 1700s, all of that stuff just looked like a little fuzzy blob. And so as he was hunting for comets, he would come across these little fuzzy blobs, and he said, oh no, I know that's not a comet because I've seen it before and it doesn't move. So he started making up a catalog of these things so that when he came across them again, he could check his little catalog and say, okay, that's not a comet, I've seen that thing before. Okay. Now these objects in his catalog were a number of different things, but some of them were what we now know to be galaxies. Okay. But what he called them were nebulae, which is Latin for cloud, and it was assumed that all of these little nebulae were just a part of the Milky Way, like a little cloudy thing in the Milky Way. And so they called them spiral nebulae, which means it was like a cloud that had a weird spiral shape. There was no way with the current technology that you could actually tell that those, like we all know that those are separate island universes of different galaxies, but they didn't know that. However, as better telescopes came along, it was clear that they were composed of stars, and therefore might be distant stellar systems. The best known of which is the Andromeda Galaxy, which is in the constellation Andromeda. It's a fuzzy patch. They couldn't tell. Anyway, I really should turn these front lights off at least. Oh, that's worse. I don't know what that does. I'm afraid that this thing sort of scares me, so I'm not sure what to.
Do it.
Do it. Huh. I think we can live with that, can't we? Is everybody okay with it? Is that too dark? Am I going to lose you now? Is it too sleepy, dark now? Okay. So I just wanted you to be able to see these pictures because some of them are really, I like a lot. And so here's the Andromeda Galaxy. It's called M31, which is Messier 31, because it was the 31st entry in his little journal. Okay. Now we know this to be the Andromeda Galaxy, but back in the day they thought it was just a little spot. And again, the picture that he had was nowhere near as good as this. Okay. And so, so things went on like this for 150 years. And then in the 1920s, people started arguing, wait a minute, these things, telescopes started getting bigger and bigger. The images that we were creating of these objects got better and better. And so in 1920, there was a famous debate, which was in Washington, D.C., called the Shapley-Curtis debate. Okay? And so they were trying to debate, are these things just little clouds or star systems in the Milky Way? And so what I'm telling you is in 1920, which, obviously is a long time ago, but it's within one human lifespan, it was thought that there was one galaxy in the universe, which was the Milky Way, and all these other things that we could see, which we now know to be galaxies, were just thought to be little clusters of stars or something like that in the Milky Way galaxy. And this was, a very unresolved, outstanding question. And so Harlow Shapley argued they must be part of the Milky Way, of our galaxy, which is the Milky Way. And Hebert Curtis, graduate of University of Virginia, argued that they're separate island universes, like that they're actually separate galaxies. Okay? Well, in the end, Shapley won the debate, but Curtis was right. Meaning, of course, we all know now that there are other galaxies. And so here they are. Apparently Shapley liked to use a lot of pomade on his hair. But Shapley is famous because he's actually the person who figured out where we are in the Milky Way, which is beyond the scope of this. But so Shapley was a very esteemed astronomer at the time. Okay, and so how was this, ever sort of overturned? Well, in 1924, Edwin Hubble used a 100-inch Hooker telescope on Mount Wilson to resolve individual stars in the Andromeda Galaxy. So the Hooker telescope, which is 100 inches across, a little over 8 feet, was the first telescope that human beings ever made. So whenever you invent a new larger telescope, you get a new view of the universe, and you can now potentially discover things that you've never seen before. And so he was able to resolve individual stars in the Andromeda Galaxy. Okay? And among these stars were some Cepheid variables. Now, again, it's beyond the scope of this lecture. Suffice to say that Cepheids are stars that we know what their power output is. And if you know what the power output is of a star, and you look at it and you see how bright it looks to you, you can tell how far away it is. So the example I use is, if I'm some indeterminate distance away and I'm shining a flashlight at you, or turn on a light bulb, and you have a light meter and you can measure how bright that light bulb looks to you, like however far away you are. Now if I call you up on the phone and tell you, oh, well the light bulb I just turned on is like a 200-watt bulb. Okay, so you now know this thing is 200 watts. You can measure how bright it looks to you where you are. Hopefully you can see that knowing how bright the thing really is and how bright it looks, you could calculate using some math like how far away I am. Because, we know the way that which light falls off with distance. Okay? And so the idea was, he found a light bulb whose power output he knew. He measured how bright it looked from, the Hooker telescope, and he was able to calculate a distance to the Andromeda Galaxy based on that. Okay? And what he calculated was a distance of of 1 million light years, is how far away the Andromeda Galaxy was. Well, back then, some people had the estimate of the Milky Way as being as big as 500,000 light years. We know now that it's about 100,000 light years. But again, back in the day, they didn't know as much as we do now. But no one thought the Milky Way was 1 million light years across. Like, that's too big. And so once he proved that the Andromeda Galaxy was 1 million light years away, that sort of settled this debate once and for all. It had to be a separate system of stars, okay, not a part of the Milky Way. And so this was in 1924, which was like the year my father was born. So it wasn't until like 1924, and obviously there's people still alive, that's like, what, 91 years ago, that we actually even fully realized that there was more than one galaxy in the universe. And I have to say, like, that doesn't seem to me that long. I mean, 91 years, I'm sure you're young people, like, that seems like forever ago, but that's like one human lifespan. And I think you can say, like, how smart as a species can we say we are if we think there's one galaxy in the universe? Now, that being said, the neutron wasn't discovered for another 8 years. Like, we haven't even discovered the neutron yet, which also seems pretty fundamental. Like, it seems sort of surprising that in 1924 we were ignorant of the existence of neutrons, you know, which is one of the building blocks of matter. Okay, so we now knew that, that there was more than one galaxy. And so galaxies, just to come in groups, and the Milky Way is a member of what we call, and I'm not, you know, of the local group of galaxies. And the local group is spread out over about 3 million light years and contains about 40 members. And what the way this works is, galaxies, like the Milky Way is a big galaxy. And it has a little posse or retinue of about a dozen little dinky galaxies that are in orbit around it. Sort of like a star and planets, but that's a completely wrong analogy, but it gives you the right idea. And so the Andromeda galaxy, which I showed you earlier, all of the stars you see in this picture are stars in the Milky Way, but that fuzzy blob and the fuzzy blob up there are two of the smaller galaxies, like Andromeda's little retinue of galaxies that orbit it. And so there's about 40 galaxies in the local group, and there's only 3 big ones. And so there's the Milky Way, the Andromeda galaxy, which is this one, and this is the other big spiral, which is a couple million light years away, which is called M33, because it was the 33rd entry in Messier's book. Okay. Now, the Andromeda galaxy, which is this, which is on your planisphere, that's the most distant object you can see with the naked eye. If you go out tonight, right after when it gets dark, the Andromeda galaxy is going to be pretty much straight up. And if you use averted vision, you can see it, and it's about 2 million light years away, meaning the light that you're seeing, if you actually see this thing, if you have binoculars, it's easy to see, left the Andromeda galaxy 2 million years ago, and it's been traveling through space for 2 million years, with its destiny being to crash into your retina and send a signal to your brain that you're seeing that light. Otherwise, it just would have hit the Earth and, I guess, just been absorbed, or something like that. Now, that being said, you won't see anything like this. When you look at it, the central core of the galaxy right there, this thing is huge. It's like 4 degrees across. The central core, that bright spot right there, is about the size of the full moon. And that would be like the only thing you see. The rest of this, there's way too low surface brightness for your eyeball to see. Like, this picture is a long exposure photograph. And so I think we all know that if you expose something for like an hour, you can see dimmer features. Your eyeball reads out about 30 times a second. So your eye collects light for a 30th of a second, then sends it to your brain, collects it for 30th of a second, sends it to your brain. That limits like how dim of an object you can see. Because you can't take a long exposure photograph with your eyes. There's nothing you can do about that. So this is the most distant thing you can see. So here's M33. That's the other part. Now this is a picture I like to use for what the Milky Way we think kind of sort of looks like. And you live about 2/3 of the way out from the center on the inner edge of a spiral arm called the Orion Spur Arm. And so we live in the Milky Way, which is one of the 3 big galaxies. Now the biggest, really big galaxy to us is the giant elliptical in the Virgo cluster. And this galaxy is about 1,000 times more massive than the Milky Way. So it's a monster, okay? And it's in the Virgo cluster, and again, we don't have time to talk about all this, but the local group is falling into the Virgo cluster. The Virgo cluster is a group of about several thousand galaxies, about 60 million light years away. And it has so much gravity that it's like dragging, the local group is like falling into that cluster. And so eventually our whole group will join the Virgo cluster. Okay, now we think this galaxy is so incredibly large because the Virgo cluster is roughly spherical, And this thing sits at the middle of the sphere. And it turns out that galaxies are cannibals, like they eat each other. Okay? And so the presumption is this galaxy is so huge because it's sitting at the center of this big sphere, and any galaxy unlucky enough to like pass near the center of the Virgo cluster gets gobbled up by this thing, and so it just sits there gorging on galaxies getting bigger and bigger and bigger. Like, we don't think it formed that large. We think it's become that large through cannibalism. So anyway, so eventually we may join this thing if we're lucky or unlucky, depending on how you look at it. Now, so if we want to get an estimate to how many galaxies there are in the entire universe, the best way of doing this that we currently have, or certainly one of the best ways, is you take a really deep picture of one direction in space. And one of the things that astronomers believe about space is that it looks the same in every direction, which means it's like homogeneous. Meaning, if you were like a, I don't know, bug, and I dropped you in milk, can you see that if you were in milk and you were looking around, that the milk, you know, assuming you were sort of somewhere in the middle, like the milk would look the same in every direction. Like it would just be like this white, you know, liquid that you were looking through. And so we think the universe, like if you look at it statistically, that every direction looks pretty much like every other direction. Again, statistically speaking. We know it's not identically the same, but the universe seems to be pretty well mixed, like the air in this room. And if you could see the air in this room, it would look more or less the same in every direction. It'd be very odd if all the air gathered up on one side and there was none on the other, right? Because there's good mixing in this room. And so what you do is, if you look in one direction for a really long time, and what happens is a telescope is a time machine. If you want to look farther back in time, all you have to do is look farther away. Because, as I said, if you look at the Andromeda Galaxy, which is 2 million light years away, you're looking 2 million years into the past. If you want to see what the universe looked like 10 billion years ago, just look 10 billion light years away, because that light has been traveling for 10 billion years. So a telescope allows you to see the past. It doesn't allow you to go to the past, but you can still see it. And so if you want to see earlier in the history of the universe, just look farther away, and you'll see back even farther in time. So what we did was, the Hubble Deep Field, they selected a direction in space where there was very few stars in the Milky Way between, on the way out. So the only stars that you see are this thing, which has this little X, that one, and then there's a star sort of in the middle. Every other little tiny piece of light you can see in this picture is a galaxy. And it's an area about 1/100th the size of the full moon, which is like the size of maybe a big crater, one of the small seas on the moon. So if you know how big the moon looks like, this is 1/100th of that size. And there's 10,000 galaxies in that one tiny little patch of sky. Now, this is the deepest exposure, certainly one of the deepest exposures of the universe we ever did. This was done with the Hubble Space Telescope, and it's 1,000,000 seconds. It's like 11.3 days. They just kept staring in one direction and tried to bring out the faintest objects that was capable with our current technology. So there's 10,000 galaxies in this one little tiny patch of sky. And so if you ramp this up, it would take, since this is 1/100th the size of the full moon, it would take something like 12 million of these fields to cover the entire sky. But you don't need to do that, because since we think every direction looks like every other direction, statistically you can argue it's exactly like this. And so if you've looked in one direction, you can argue that you've looked in every direction, or at least statistically speaking. And if you do the math of all that, you find out that there's about 127 billion galaxies in the universe. Okay? So, when my father was born, there was one galaxy in the universe. Now there's 127 billion. That's a pretty big increase. I think we can all agree. Okay? And so people started looking at this and they started saying, well, so how do we, so again, what we're trying to do is explain why did we come up with the Big Bang Theory. Well, sort of the very first notion that came about this was in 1912, and this is before they even realized there were other galaxies. Some people suspected it, others didn't. The American astronomer Vesto Slipher, and Vesto Slipher, that's like one of my favorite all-time astronomer names. Like, how come nobody names their kid something like Vesto Slipher anymore? well, I guess slipper you can't change. Okay, and what he did was, he was measuring the spectra, which is taking the light from a galaxy and putting it through basically a prism and looking at it, of about 40 faint spiral nebulae. Now, these weren't even known to be galaxies yet, okay? And what he found out, that almost all the galaxies showed a redshift. And redshifting is due to the Doppler effect. There's two types of things that are due to the Doppler effect, which is a blue shift, and that's if something's coming towards you, and a red shift if it's going away from you. And everyone knows this from like sitting by the side of the road or train tracks, that when, let's say a car or a motorcycle goes by, what you hear is like, "Eeeow," like that. Well, as it's coming towards you, the pitch gets higher. That would be a blue shift, because with light, blue wavelengths are the shorter wavelengths, and so that's a higher pitch in terms of sound. And when it goes away from you, in terms of sound, it goes to a lower frequency. That's why it goes, okay? But in terms of light, it gets shifted to the red part of the spectrum, which is to longer wavelengths. If you've ever gotten a speeding ticket, it was probably due to the blue shifting of radio waves. When the police officer pointed a radar gun at you, he broadcasted at a certain frequency. Since you were going into those waves, he got them back at a higher frequency, and they can tell by the difference in the frequency how fast you were going. Okay? So what he found out is, if you know nothing about galaxies, which they didn't at this point, you might imagine the universe is sort of like the air in this room. And if you could see the air in this room, I think you can see, since it's milling about turbulently, that about half the air would be coming towards you, if you could see it, and about half would be going away from you, because it's just sort of, mixing around. Now some of it wouldn't be coming towards you, away from you, but that's the idea. And so, not knowing anything about this, you might expect, if you started looking at galaxies and you thought the universe, things were just sort of milling about, maybe like air in a room, you would expect about half of them to be coming towards you and about half of them to be going away from you. See, that's not at all what he found. What he found was, basically every galaxy, which was a cloud, was red shifted, which means it was moving away from you. So this would actually be very surprising if you found out that all the air in this room was moving away from you. That would actually be a bit of a problem, because eventually where you are might have no air, like if it's all moving away. Okay? Now, this indicated that galaxies were moving away from our galaxy. Now, the problem with this is, one of the reasons why you've never heard of Vesto Slipper is he didn't publish a paper about this. And if you don't publish a paper, I like to bring this up, if you discover something but you don't tell anybody about it, it's just like you never did it, effectively. So, for instance, if I cure cancer tonight, like experimenting in my house, and then I never tell anybody about it, and then I die however many years in the future, even though I've cured cancer, like I didn't cure cancer, because I didn't tell anybody. Like they might dig up my papers and say, "Oh, what, this guy, he cured cancer, but he never told anybody about it." Like I'm not going to get any credit for that. Matter of fact, I might be somewhat, maligned for that. Obviously, if I could cure cancer and didn't tell anybody about it, that would be pretty bad. So, but this guy found that all these galaxies are moving away, and just for whatever reason, decided not to tell a bunch of people, so he gets no credit. Okay. Now, if almost all the galaxies we see are moving away from the Milky Way, what does that tell us about our location in the universe? Now, I'm not going to try to drag this out of you because I have a lot of ground to cover, but a lot of the people, like when they first saw this, thought that it meant that we were near the center of the universe. Like if everything's moving away, that seems like you're in some sort of privileged position because everything's moving away. Okay? Ultimately, the answer to this is, we'll find out, it tells us nothing about where we are in the galaxy. Because we realize that no matter where you are in the universe, everybody would see exactly the same thing. Well, if everybody sees exactly the same thing, I think you can see that doesn't really give you any information about where you are. Okay? And so then along comes Edwin Hubble, who is, I argue, is like one of the, I'm not a huge Hubble fan. I don't want to make you my biases. But like Hubble, like for instance, when he does this, he sort of repeats Slipper's experiment and gets credit for discovering that the universe is expanding, but like he didn't even realize he discovered that, like when he published a paper, really. The other thing about Hubble that I hate to bring up, but I always do, is like he was like a Rhodes Scholar, and he went to England for like a year, and then he came back to the United States and spoke with an English accent for the rest of his life. Which I don't know, for some reason that just rubs me the wrong way. I don't know, it just seems sort of, I don't know what. The other thing was he claimed he was like a World War I war hero, but during World War I he was teaching high school like in Ohio. So I mean, I don't know what to say about all that, but yeah, it just seemed like a little bit odd to me. But so anyway, but that being said, he was one of the preeminent observers, certainly of the 20th century, and just happened to be at the right time. So he used the Hooker telescope, found out the Andromeda galaxy was a separate galaxy. That was huge. Now we're going to find out Hubble is going to discover the expansion of the universe because Slipher couldn't be bothered to write about it. So here's the telescope he's using. Okay. And in the late 20s, Hubble and Milton Humason began a systematic survey of the distances to nearby spiral galaxies and their recessional velocities. And in 29, they published a paper showing that the recessional velocities, which is how fast something is moving away from you, is directly proportional to their distance. So which is weird about this is that if a galaxy is 1 unit away from us, it's moving at some speed. But if another galaxy is twice as far away, it's moving twice as fast. And if it's 3 times farther away, it's moving 3 times as fast. And if it's 4 times farther away, it's moving 4 times as fast, etc. It's almost as though the galaxies know how far they are away from us and therefore know how fast to be moving. This is a very surprising thing. And it's one of the 2 fundamental facts that if you come up with any theory of the universe, you would better explain, like one of the requirements is you have to explain how do galaxies move away from us with a velocity directly related to their distance. And like, you know, and ideally you come up with a theory that doesn't invoke, oh, well the galaxies know how far they are away from us, therefore they know how far and fast to be going, because that makes absolutely no scientific sense. Okay? And so what he did was, so if you plot up, so if you look at these things, the length of this arrow is the red shifting, is how far the lines have been moved. And what you can see here, and these are distances that, and you can see from these pictures that we assume that all of these galaxies are basically the same size, but you can see that as, so the distance up there is 18 megaparsecs, it's like 18 units of distance, 230, 330, etc. And what happens is the length of this line increases directly with that distance. Okay? And so this was a very surprising. So here is the graph he published in the 1929 paper, where he's got distance here, forget about the units, and the velocity there, and you get a pretty good linear relationship. Okay? Now this was extended out. So this was the sort of original data, but if you extend it out, and so now this is if you extend it out to great distances, which people did to try to see, well, how does this keep going if you look farther and farther away? Does this still work? And the answer is yes. If you find a galaxy that's 10 times farther away, it's going 10 times faster. If it's 20 times farther away, it's going 20 times faster. Okay? And so this is very curious. And so people started trying to figure out, well, how can we explain this? In other words, what is some scientific idea that can explain why the universe behaves like this? And since this is a straight line and it comes out of the origin, I'm not going to try, this isn't math, but you guys, almost everybody, one thing you can count on is people know that the equation of a line is like y equals mx plus b. Like where y is the y-coordinate, m is the slope, x, and b is the y-intercept. Well, because this comes out of the origin, you can get rid of b, and so it's just that the formula is y equals m times x. So there's some slope. So the y-coordinate is equal to some slope of this line times the x-coordinate. Well, in this formula, the y-coordinate is the velocity, the x-coordinate is the distance, and the slope of that line, like in other words, how steep that line is called the Hubble constant. And what it is, it's a measurement of how fast the universe is expanding. If that line was steeper, okay, then the universe would be expanding faster. If the line, in other words, had a higher slope. If the slope was lower, then that would mean the universe is expanding at a slower rate. Okay? And so this relationship, this is called Hubble's law, that is one of the 2 fundamental things we know about our universe. Okay? As astronomers, The Hubble law tells us something very important about the way the universe behaves. It shows us that things are moving apart with a velocity proportional to their distance. And so you have to come up with an idea that explains that, hopefully without invoking previous knowledge of galaxies, knowing their velocities and things like that. Okay? And so the slope line of d is the distance, and this is called the Hubble law. Now, the most accepted value of this, and astronomers use weird units, and I hate to get bogged down in units, okay, is 71 kilometers per second per megaparsec. Okay, I realize that's, so what that means is, a megaparsec is a unit that astronomers use. You've probably heard of light years. A light year is the distance that light will travel in 1 year going at the speed of light, which is about 6 trillion miles. Astronomers have these other units called parsecs that we use, and a megaparsec is about 3.3 million light years. Okay, so what this means is, if some galaxy is a megaparsec away, which is 3.3 million light years, then it would be moving away from us at 71 kilometers per second. Okay, and so now if you convert this into units that may be a little bit more familiar, but I'm not sure if it actually helps. If you wanted to convert this to miles per second per megaparsec, per million light years. So a million light years is about half the distance from us to the Andromeda galaxy. It would be about 13.5 miles per second per million light years. So what that means in terms, but I'm not going to use those units, I'm going to come back to that in a second. So the Hubble law simply states that a galaxy moves away from us at a speed of 71 kilometers per second for every million parsecs. So if a galaxy was at 1 megaparsec, which again is like 3.3 million light years, it would move 71. If it was 2 megaparsecs, it would be 142. If it was 5 megaparsecs, it would be 355, which is that times 5. And so the idea is, if you're 5 times farther away, you're going 5 times faster. And this just gives you the number, well, how fast are you actually going? Okay? And so the answer is 71 kilometers per second. That's about 50 miles per second-ish per megaparsec. Something like that. Okay? Which is, pretty, 50 miles per second, I think we all agree, is, pretty fast. Okay? And so what happens is so how do we explain this? Okay? Well, it turns out that if everything is moving away from us, the only natural way to explain this is to say, okay, well, think of it this way. The universe today is bigger than it was yesterday, right? Because, the distance is. What about if we go back 2 days ago? What happened to the size of the universe? It gets smaller still. If we go back a year, smaller, right? Go back 100 years, it's even smaller. And so what this tells us is that if you run time backwards, the universe shrinks. Well, if you run time forwards, that means that the universe is getting bigger. Okay? And so the Hubble law implies that the universe is expanding. So what I'm telling you is that, and I'm jumping forward a little bit, this formula right there is what gave rise to the Big Bang Theory. Because the universe is expanding. So how can you explain that? Well, you can explain it by the origin of the universe being some type of explosion. Now, it's going to be, not really an explosion. But so the fact that the universe is expanding gave rise to the Big Bang Theory, because if you run time backwards, then the universe keeps getting smaller and smaller and smaller and smaller and smaller and smaller and smaller. Well, you can't do that forever, because the universe can only get so small. So if the universe is getting bigger now, if you run time backwards, it all has to compress down, keep getting smaller and smaller, and eventually it all compresses down to 1 point. And so the notion that, that the universe started from this 1 point and started this expansion is what gave rise to, the Hubble law is ultimately what gave birth to the Big Bang Theory. Okay? So at first that all the galaxies are moving away from us seems to indicate that we're at the center of the universe. However, in a uniformly expanding space, every galaxy is moving away from every other galaxy. And so the best way to explain this is not that there was some explosion, as we'll talk about, is that the way the Big Bang Theory accounts for this is not that galaxies are moving away from us. Okay, that's not really true. I mean, it is, but it's not. What the idea is that if you have two galaxies that are a certain distance apart, that galaxy is not moving away from us because it's actually moving, but because the space between you and that galaxy is growing. In other words, the universe is like in a copy machine that's like an enlarging machine. And every second, what happens is, like the distance between two objects, so the universe is inflating from the inside out. Like distances are getting bigger. Okay, now this helps because if you have a distance of 1, which would be like 1 megaparsec, that's growing at a certain rate. But if you're 2 megaparsecs away, you've got two boxes that are both growing. And if you have two boxes growing at the same rate in the same amount of time, then you'll be going twice as fast. If you have 3 boxes, so I do this with like a little analogy. So let's imagine we have a rubber ruler with 4 ants on it, and that the ruler is expanding so it doubles in length every minute. So we're stretching this ruler. Consider the distances. Well, I'm not, from between the different ants. So if you have this ruler. Or you can also think of it, might be easier to think of if you put like some dots on a piece of elastic or a rubber band and you stretch it. Can you see that if this ruler gets stretched, that the distance between all of these ants is increasing? That's because the actual size of a centimeter is getting bigger. Okay? And so not only that, this first ant right here, if everything's doubling in 1 minute, this ant here at 4 was originally 2 centimeters away, but because it was originally 2, but it's doubling, it's now 4 centimeters away. And so this first ant you would see moving at 2 centimeters per minute because it would take 2 minutes for that distance to double. If you take this other ant, which is at 7, since there's 5 centimeters between it and they all doubled in size, that one at 7 it has gone up by 5 centimeters, and so it's going 5 centimeters per minute. And the one at 12 is going 10 centimeters per minute. In other words, since every part of the ruler is getting bigger, the more parts of the ruler you have between you and one of these other ants, the more growth you will have during that minute. Now what I'm telling you is this is exactly how the universe is expanding. Like you can imagine these ants are actually galaxies, and the space between them is stretching, and therefore they all appear like they're moving away from us. Those galaxies really aren't moving. It's just like if I put dots on a rubber band and stretched it, the dots really aren't moving relative to the band. But because the band is getting longer, they are moving apart. So the galaxies are stationary, but in an expanding space. Now, why do I say, I'm saying this as though I think it's fact, but what I'm telling you is this is how the Big Bang Theory works, and it explains the Hubble law in a very natural way. I mean, nobody's been able to come up with a better reason why galaxies move away from each other with a velocity proportional to their distance, other than saying that the universe is like a giant stretching rubber ruler or rubber band, and everything's getting bigger. Because it naturally explains why things that are farther away are moving faster. No other explanation that anybody's ever been able to come up with can account for the Hubble law in such a sort of simple way. Now, that's not saying that somebody couldn't come up with a better idea. What I'm saying is that as all the collective human thinking about this, the fact that the universe is expanding is the best thing we've been able to come up with. So as the ruler stretches, do all the ants see the other ants moving away from each other? And the answer is yes, because since the space is expanding, every single ant will see basically exactly the same thing. They'll all be moving away from everybody else, all the other ants. Which is why in the universe, all galaxies would see all the other galaxies moving away from each other, because the space between galaxies is getting bigger. Okay, now again, why that's happening, I don't know. I mean, that just seems to be the way, we think that it's happening because it's the best explanation we can come up with. And the way science works is you see something happening, you make up some crazy idea to explain it, then you test that idea as best you can, and If nobody can come up with a better idea, at least for the meantime, we say, well, that crazy idea that somebody made up about the universe expanding, like the distance between galaxies is getting bigger, like we think that's real now, even though it was just like a completely made up idea. I mean, Bohr did the same thing when he tried to explain why hydrogen, like he said, well, let's just pretend that electrons can only orbit at certain levels. Why, I don't know. Let's just pretend that. If we do that, then we can explain the way atoms behave. And so then later on, Bohr said, well, you know that crazy idea where I just made up that electrons can only be at certain levels? Like, I think it's right. Right? And that's the way you test ideas. I mean, they're all just made up things that people think. It's not like, you know, somebody whispered in our ear, oh, this is the real truth of the universe. Like somebody just made it up. Then if you stand the test of time. So it says, the ants are farther apart now from each other with a greater velocity. So that we're further apart, move away. So the speed at which the distance recede is proportional to their distance, just like the Hubble law. On this ruler, all the ants will see all the other ants moving away from each other, just like galaxies in our universe. So the universe is expanding like this ruler. Now I'm just going to quickly, because we always run out of time before. If you want to look at a three-dimensional analogy of this, because now we're on a ruler, if you imagine raisin bread, you have raisins like put in this dough in rising bread. Regardless of which raisin you pick, all the other raisins are moving away from it. The reason is because when you cook the bread, like the dough expands, like the bubbles in the dough, one way to think of it, get bigger. And if the dough is expanding uniformly, then everything that's lodged in the dough is going to move farther away from everything else. Okay, and so if you take this, so the space, you know, since the dough is rising uniformly, all of the raisins in raisin bread would be moving away from all of the other raisins. Okay, and so this is more like really like the universe because it is, you know, three-dimensional rather than being like a rubber ruler that you're stretching. Okay, and so the universe is inflating from the inside out. So the Hubble law expansion of the universe increases the distance